the students who are on the, especially the ones on the earlier part of the learning curve, if you see something that isn't clear and you'd like to know, don't be that shout out. But if we don't finish, it's more important that it can be helpful to what we're saying than for us. But as I'm sure all of the students of that position appreciate, that a lot of times you may not understand something the first, second, third, fourth time you hear it, but the more often you hear it, the more things you get to interrelate. And from your practical experience, you learn more than you will from just this kind of academic lecture. But many of the speakers are presenting the same concept, so I think it's the whole experience more than any one lecture that's going to be most helpful. But please do ask questions if there is something that you can recognize you'd like to have elaborated. I'm going to start with some very basic concepts, reminding you that the important thing about a Fourier transform is that any object, this is of course just a one-dimensional arbitrary trace, but any object can be thought of or can be represented as the sum of a bunch of different sine functions or cosine functions. So here's three different cosine functions. They are a slow one, a medium one, and a fast one. And the period of each of these is a fraction of an integer fraction of the period of the slowest one. And so we say that these sine functions are harmonics of the fundamental. The periodicity is 1/10 that of the slowest one. So just like in music, they're harmonics of a fundamental tone. But we're talking about space. And this, if we add these up, you get this periodic repeating motif, but within one unit cell of this motif, there's nothing periodic about it at all. And as we transition from this simple case of just three terms, we go 4, 5, 6, n, very large number, and the increment of frequency, the increase in frequency of oscillation, comes closer and closer and closer, we will go over from just a sum to a continuous sum of integral. And this integral, which is nothing but a sum of the sine terms, that integral is the Fourier transform. And very basic things. The sine functions are completely defined by two parameters. One is the amplitude. So here's two sine functions that have the same period. The maximum and minimum occur at the same places, but they have a difference of amplitude. So when you talk about Fourier amplitudes, that's what you need, is the height of that sine function. But the second parameter that then completes the definition of a sine function is the phase. And here I have two copies of the sinusoidally varying function that have the same amplitude, they have the same period, but one is shifted from the other. So when we talk about the phase of a structure factor, this is what we need, that one is shifted relative to the other one. Origin for one Fourier term is shifted by some amount relative to the origin of the other sine function. And then, to complete this, I have an example of two functions that have the same phase. They start at their maximum at the center of this coordinate system. They have the same phase. They also have the same amplitude, but they have a different frequency. And so, although they start out together, they begin to separate because one is oscillating more frequently than the other. And these basic ideas of the individual components of a Fourier transform, I find it quite helpful to go back and review these basics. Now, of course, we talk over and over and over again about the resolution of our structure. And it's all not already very prominent in on your radar screen. The resolution increases with the frequency of the sine term that's included in this summation. So this first fundamental or low resolution feature has a very long period, and then as we get more rapidly oscillating terms in the Fourier sum, the resolution will improve, and then the highest ones be the highest resolution features in a complicated structure. So resolution and spatial frequency, which is the reciprocal of the period. If you have a periodic function, then you also speak of its frequency. So resolution and spatial frequency are the same thing. They're just, one is common sense language, the other is mathematical jargon. But they are exactly the equivalent terms. So I told you that when we have lots and lots of sinusoidal functions and their frequency differ by only a very, very small increment, we transition from a sum into a continuous sum or an integral. So this is the definition of the Fourier transform. Our object is characterized by some Coulomb potential. So I use the function capital V for the Coulomb potential of the protein molecule. And if I multiply that by a generalized version of a sine function, the complex exponential, so it's a harmonic function just like the sine or cosine. So multiply that by the most general form of a harmonic function. And that harmonic function is characterized by a frequency, S, spatial frequency. But of course, in its argument, it also has the real space variable, not integrate over the real space variable. That is the Fourier transform of the Coulomb potential. And this Fourier transform picks out the value of the amplitude and the phase of that sine function. So the sine function has a frequency S. S occurs only once in this definition of a Fourier integral. If I took a different S, then I would get the amplitude and phase for a different spatial frequency. So if I could choose what spatial frequency I would like to know the value of the amplitude and phase, put that into the integral in the computer, of course, compute the integral, and that will give me a complex valued function that I can represent as a real valued amplitude and complex function e to the I, the phase. Phase, remember, is the origin of that sine function relative to some standard. So you choose where the center of the coordinate system is in Fourier space. You don't choose that. So I'm wandering off the subject here. I'm just going to stick with the assertion that this integral gives you the relative phase of each term in the Fourier transform. So B could be the Coulomb potential, or it could be the image intensity. So electron diffraction computes the Fourier transform of the Coulomb potential. You record an image, that's a real valued function. You digitize that, you compute the Fourier transform of the image, then you get the amplitude and the phase of each Fourier component in the image. So diffraction patterns, whether they are optical diffraction patterns of an image or they are computed. Diffraction patterns, in this case it's also an electron diffraction pattern of the Coulomb potential. Diffraction patterns are all Fourier transforms. I should qualify that by saying Fraunhofer diffraction patterns. But what we commonly think of as a diffraction pattern is a Fourier transform. And so in an electron diffraction pattern, or in a computed diffraction pattern of an image, let's say, every diffraction spot represents a different spatial frequency. And the amplitude, so the amplitudes of these spots vary quite a lot, from bright ones to dim ones. And if I go to any particular spatial frequency, the amplitude there is unique to the structure of the object. And of course the phase. Point that you hear mentioned over and over again. When such a diffraction pattern is obtained by a calculation in a computer, then you still recover from that calculated Fourier transform the phase at each of the spatial frequencies. So when this diffraction pattern is produced by electron diffraction or by optical diffraction or photographic negative, you record that Fourier transform on a detector that only detects intensity, and that's why you lose phase. But when you compute it in a calculation, there is no physical problem involved with having to record the intensity. So that is how you recover the phase. Now, there's a theorem of Fourier transforms called the projection theorem. And it says that when a three-dimensional object is projected, here's my, let's say, monolayer crystal that has some finite extents in the third dimension, it's a molecule. And when I take an image of it, that image is a projection of the structure. And so when the three-dimensional object is projected, you get a two-dimensional image. The Fourier transform of the two-dimensional image is not a projection. The image itself is a projection. The Fourier transform is a slice. So here we are in real space. Here we are in a sort of frequency space called Fourier space or reciprocal space. And we're going to have projections in real space and planar slices through the three-dimensional Fourier transform when we compute the Fourier transform of such an image. And we can tilt the object, and when we tilt the object, the direction of the slice that corresponds to the Fourier transform changes. So we get a whole lot of different two-dimensional slices and gradually build up the value of the three-dimensional Fourier transform that's represented by this set of lines here. Once we have, as it were, reconstructed the three-dimensional Fourier transform, then we just ask the computer to please do a three-dimensional Fourier transform back from all of this data, and it gives us the structure. Unfortunately, it doesn't draw in the ribbon diagram and the helices, etc. You have to do that part yourself. And of course, you have to have a high enough resolution reconstruction to be able to do that. So, to summarize, when one of these slices is called a central section, and when a central section through Fourier space, it always goes through the origin of Fourier space. And when data from many such central sections are combined, you build up the full three-dimensional Fourier transform of the object. And Fourier transforms, I didn't make this point before. One of the things I like to say about when you're typing something on your computer and you wish you hadn't deleted something, you can hit the undo button and it comes back again. And the Fourier transform is essentially its own undo button. When Fourier space, we don't really understand things that we see in Fourier space. We understand things that we see in real space. And so we can pop back and forth between real space and Fourier space just by hitting the undo button. And this slide actually makes that point. So information about the object is exactly the same. It's neither more nor less in one space than it is in the other. In real space of this diagonal or in reciprocal space of this diagonal. So previously I introduced the Fourier transform as being the integral of the cooling potential multiplied by a complex harmonic, integrate over all of real space, and that gives you the amplitude and phase at that particular frequency. And I do it for many different frequencies. Similarly, once I have the amplitudes and phases for all of the frequencies. That now is a three-dimensional function. Multiply it again by the inverse. Notice the change in sign in the complex exponential. And now integrate over all of reciprocal space to give back values at any chosen value of real space, x. So x enters in only in the argument of the exponential in this inverse Fourier transform. There's a couple of mathematical theorems that are used over and over and over again in understanding images and in image processing. And one of these is the so-called convolution theorem, and it says that if we multiply two different functions pick real space or reciprocal space, it doesn't matter. I'll pick real space. I have two functions in real space, and I'm going to take the product of these two functions. You might wonder, why would you do that? We'll see the applications shortly. So I have the product of two functions, and I take its Fourier transform. The result in reciprocal space is a different kind of product that is called the convolution product. And the convolution product, or we simplify it, we just say it is the convolution of those two functions. The convolution product is mathematically not intuitive at all. So big F is the Fourier transform of little f, big G is the Fourier transform of little g. And their convolution product involves a real multiplication of the function f times the function of g, but one of these has to be shifted. It goes to a different frequency. So if f is being evaluated at the frequency s prime, then g has to be evaluated at the frequency s minus s prime. And then you integrate over all possible values of s. So we take one function, and the other one, we shift them, multiply them together, and get the area under the product, area under the curve. And then we shift it by another amount, and another amount, and so forth. And gradually we map out a full new one-dimensional function, two-dimensional, whatever S is. S could be one-dimensional variable or a three-dimensional variable. So this is the not very intuitive idea of convolution, but I'll show a couple of examples. You can get the idea that things are going to be smeared out by this convolution. So f and g are shifted relative to one another, and you find the area under the curve. And you do it over and over again until you wind up with a new continuous valued function. There is another aspect about the convolution theorem, which again, starting in real space, f and g are in real space, and suppose I had convoluted little f and little g in real space for some reason, and now I compute its Fourier transform. That will give us something easier to understand. It gives us the product, just the multiplication of big F times little f. And this becomes enormously useful information in understanding many things about image formation and about the way that data are processed in crystallography. So I indicated that convolution generally broadens the original object. So here I have a little rectangle function, 0, 1, 0. And if I convolute it with itself, so imagine taking this rectangle function and another copy, and if I superimpose them on top of each other, nothing changes, and I get a number. It's the area under this curve. But if I shift it, the overlap is less. And so the area under that product will be a little less. And you can intuitively immediately see that that operation, the convolution of a step function with itself, will give you a triangle function. And the full width is now from minus L to plus L, whereas original one went from minus half L to plus half L. So the convolution of a rectangle function with itself results in a different shaped function. It's also a broader function. So that's a good anchor point. If you're not already quite familiar with the idea of convolution, if you can remember this example, it will help you to get back to a kind of mathematical understanding of what convolution is. A second example that's enormously useful is when a function can be quite complicated, a bunch of sausages and a low resolution image of a protein molecule. This is just an arbitrary function. When a function is convoluted with a single point, a mathematical point, we'll call that a delta function. And if you're not already familiar with it, as you go through the practicals, you'll know about Kronecker delta functions and Dirac delta functions. Don't worry too much, just think of them as points. When we convolute this arbitrary function with a point, if you think of this operation of multiplying, shift, multiply, integrate, shift, multiply, integrate, you'll quickly appreciate that convolution with a point makes a copy of this function wherever that point is. So if I convolute with the point at the top left, I will get a copy of this guy. If I convolute with the point at the bottom right, I'll get a copy. So wherever there is a point, you'll get a copy of this basic function. Therefore, it turns out to be quite powerful in crystallographic data processing to say, I'm not going to think of my crystal as a crystal. I'm going to think of this crystal as the convolution of the unit cell with a lattice function. And once you, that becomes an easy concept, then a lot of crystallographic data processing will make a lot of sense. So I could ask the question, how is the Fourier transform of a two-dimensional crystal related to the Fourier transform of one unit cell? Answer would not be so obvious. It might be, there's diffraction effects. It's going to be mysterious. I don't know what it's going to be. But if you understand it from the point of view of the convolution theorem, it becomes really simple. So the Coulomb potential for a 2D crystal, I explained, is the Coulomb potential for one unit cell convoluted with a two-dimensional lattice of points. And the Fourier transform of one function convoluted with another is a product. So the convolution of the 2D crystal is therefore the product of the Fourier transform of one unit cell with the Fourier transform of a lattice of points. The rabbit that I have to pull out of the hat to make sense is the additional information that the Fourier transform of a lattice of points is a lattice of parallel lines. So the Fourier transform of a two-dimensional lattice of points that's periodic. So the Fourier transform, you can appreciate, is going to be periodic in the same dimensions conjugate to the real space periodicity. But in the third dimension, where the lattice of points is not periodic, it doesn't repeat, the Fourier transform is going to be continuous. It's not going to be sampled in any way. So think of this lattice of parallel lines as a comb, or better, a brush. Lots of parallel lines. And the Fourier transform of a two-dimensional protein crystal is a regular array, a repeating array of what I call one-dimensional samples. So these on my comb are parallel, repeating parallel lines. And I'm multiplying this times a continuous Fourier transform of the protein molecule. That means I'm sampling the continuous Fourier transform. So I might like to have the Fourier transform of the whole molecule, but what I'm going to get from the crystal is going to be samples. So on this continuous set of reciprocal lattice lines. So here is an attempt by Chuck Sindelar to an artist's representation of what's going on. In reciprocal space, spatial frequencies here, there's one plane where he's drawn this array of points, but they're really, the three-dimensional Fourier transform is extended above and below the plane of these points, as indicated by a few of the reciprocal lattice lines. And he's then added to that intensity shading to indicate that the amplitude of the Fourier transform goes up and down. It's intense in some places, weak in other places. And the way that it goes up and down varies from one reciprocal lattice line to the next. So if this were a protein crystal, we would say there is an A star, a B star direction, and a continuous variation in the third dimension. And we would index our diffraction spots H times A star plus K times B star. We'll learn about that in the practicals if you aren't already familiar with it. Electron microscope images, if they were absolutely perfectly projections, would, by the projection theorem I mentioned before, would sample this comb function or brush function on a central section of plane. Normally, you don't have to worry about it, but when you get to really high resolution, and if your crystal is somewhat thick, you have to worry about the fact that electron microscope images are not absolutely perfectly described as being projections. And as a result, we have to somewhat generalize the idea of the projection theorem to say what happens if it's not really a projection. Then we sample not on a plane, but on a spherical surface that is closely approximated by a plane. And this spherical surface that goes through the origin comes from the theory of X-ray crystallography, and a mathematical crystallographer whose name is Ewald realized a construction to describe what you get when you make measurements that are not really represented as projections. So this is called the Ewald sphere. It is just as good a concept, it's just more complicated. For all of us, we never worry about the curvature. We always treat our images as projections and the Fourier transforms as central sections. And only with good fortune do we get to high enough resolution that we have to start to worry about curvature of the Ewald sphere. But the software that you will use will not worry about that. So I've actually used up my full half hour, and so I will not launch into the secrets of the fast Fourier transform or describe how the cross correlation function, which is used a lot in unbending, for example. I'll just leave it at this and say it's a special example of convolution, which I'll describe.
You have 40 minutes if you want.
Oh, I do have 40 minutes. I see. Okay. So I will continue, but it's a good chance anyway to pause and ask